Welcome to Let's Get to the Marks, going through the A-level chemistry paper two, organic and physical chemistry. Sorry there, just checking my mic was on. Yeah, going through the 2024 paper two for AQA A-level chemistry. It's the organic and physical. You got 2 hours. Woo, 11 questions, quite a lot for a paper. Let's go. Let's get into it. So don't forget at the start of each question, press pause on the video. You might want to listen to me read out the stem, but then press pause on the video, grab a pen, grab a paper, grab your calculator and have a go. All right, I'm going through the questions. So question one, propanone reacts with bromine in alkaline conditions. And we have the equation here, CH3COCH3 plus Br2 plus OH minus goes to CH3COCH2 Br2 plus Br minus plus H2O. The rate equation for this reaction is rate equals K, and then we have propanone and hydroxide ion concentration in the rate equation. Sketch a graph on the axis provided to show how at constant temperature the concentration of bromine changes during this reaction. So why don't you pause the video, grab a bit of paper, sketch a line, and then unpause and see if you got it right. All right, I'm going to go through it. So at first we might think, oh yeah, like most reactions where the reactants are important, where they're part of the rate equation. What would happen is initially when the reactants are at highest, the reaction rate would be fastest. So we would see the concentration of the propanone decrease rapidly at first. And then as there are less, we'd expect the bromine particles to decrease rapidly at first. And then as there are less bromine particles available to react, there's less probability of a collision. And so we would expect to see this kind of curve. Like over time, the reaction gets slower or the rate of reaction gets slower. And you can work that out from the gradient. However, because bromine here is not in the rate equation, then it is zero order with respect to the reaction. And what that means is that the rate of the reaction is not dependent on bromine and it doesn't change. So essentially, regardless of how much bromine there is, what the concentration is, as it goes down over time, it does not affect the rate of reaction. And we know that because it's not in the rate equation. And this is the sketch for concentration against time for a zero order reaction. So the gradient stays the same all the way down, which means the rate, the concentration over time is staying the same all the way down. It's zero order. Okay, that should get you a mark if you got it. Well done. And let's move on. Oh, 5 marks. That's quite a lot for a question on your second part of the paper. 1.2. Table 1 shows the initial rate of this reaction for experiments using different mixtures containing propanone, bromine, and hydroxide ions. Experiment 1, experiment 2, experiment 3. And you can see what they've done. With each experiment, they've changed one of the three reactants and they've done the initial rate. Okay, complete table 1. Use data from experiment 1 to calculate the rate constant K for this reaction. Give the units for the rate constant. So possibly what I'm going to do first of all is use data from experiment 1 to calculate the rates constant K for this reaction. Okay, so you can see I've written out the equation here. So rate equals K. We've got the propanoic acid, propanone, not propanoic acid. It's a ketone, propanone concentration and the hydroxide ion concentration. And we want to find K. So what do we want to do here? We want to rearrange this. So this is where you get to practice your rearranging skills. And in order to isolate K, we're going to divide the rate by the propanone times the hydroxide. So we're going to go rate. And now all we want to do, that is going to rearrange to get K. Now we just want to substitute the numbers in. So we're going to substitute these in to work out K. So 2.75 times 10 to the 11 over 1.5 times 10 to the minus 2. And that is the propanone concentration multiplied by 2.5 times 10 to the minus 2 is the hydroxide concentration. Now we don't need to include the bromine because it is not obviously in the rate equation. So some of you might be able to just whack that and keep it all in your calculator. But if you find that difficult, what I suggest you do is you do the 1.5 times 10 to the minus 2 times 2.5 times 10 to the minus 2 first. And what you'll get if you do that is 2.75 times 10 to the 11 over 0.000375. And if we blah, bloop that in the calculator, you're going to get like whatever that is. Yeah, that is pretty disgusting, the amount of zeros. I wouldn't be surprised if I got that wrong. So that is like 7 point Oh my gosh. That's just disgusting. Let's write that instead as 7.3 times 10 to the minus 8 because there's like 8 zeros in front. I hope I've done enough zeros. I'm not even going to count. It's making my eyes hurt. Right. So how many marks would we have got so far? Well, we've used the data in the experiment to calculate the rate constant. So that is going to be at least two of the marks for that middle bit there. Possibly three, and then we need to complete the table and we need to give the units for the rate constant. Now I'm going to show you how to work out the units for the rate constant. So our rate constant is 7.3 times 10 to the minus 8. Now, how do we work the units out for this? So this is a little bit that comes up in every single exam. You can be guaranteed you're going to be asked to do the units in your exam. And this is what you do. You're going to say, well, rate is in, you can see the units, they're right up here, right? So rate is in mole, dm, oh my gosh, minus 3, s minus 1. And that's over the top of mole dm minus 3 and mole dm minus 3, over the top of these two, right? So this is how we're going to work the units out. And I'm going to show you how I do it. There's actually quite a few ways to do this. So, and I vary my ways depending on which walkthrough I'm doing, because just like a bit of variation. So what I do is I add these all up, add up whatever you've got over here, and then just subtract from the top what's on the bottom. So what do I mean by that? Well, it's going to be mole dm, oh my days, minus 3. I think I've got this pen on a bit of a fat one. No, did it? And then I'm going to subtract from that. I'm going to add these together. So I'm going to take away from that mole to the 2 to the dm minus 6. And when I do that, you're going to get mole minus mole 2 is mole to the minus 1, because you've gone mole minus mole 2, mole to the minus 1. Then I'm going to go dm minus 3 minus minus 6. What do you get if you get minus, so I'm basically going to go minus 3 minus minus 6. And of course, that's going to make a plus. So I'm technically adding 3 to minus 6. So what I'm going to get is dm to the minus 3. And then the s to the minus 1, well, s to the minus 1 minus nothing. We're not taking anything away from it. So it's just mole to the minus 1, dm to the minus 3, s to the minus 1. And they are your units. So we're going to give ourselves a tick for that. Now I need to get a mark for each of these. And what I'm going to do here, guys, there's two ways to do it. So look, we could bash these into the rate equation and rearrange to find hydroxide ions, right? Because we now know K is 7.3 times 10 to the minus 8. We now know what the propanone is here, and we know what the initial rate of reaction is here. So we can whack that in and we can find the hydroxide ions. But there's a simpler way. If you check out this equation, what order are hydroxide ions? Well, they're going to be first order. Okay, and you know that because there's nothing outside the brackets. If there was a little 2 outside the brackets, there'd be second order. But these are first order. So what does this mean? This means that whatever you do to the hydroxide ions, you do to the initial rate, or whatever's happened to the initial rate tells you what's happened to the hydroxide ions. So when we go over here and we look, they haven't changed the only other reagent that will affect the rate. Okay, so that's in the rate equation. They haven't changed that. So any impact on this initial rate, and we can see something has happened to it. It looks like it's increased by how much, we'll find out in a second. That has all been caused by the hydroxide ions, and it's first order. So whatever's happened to that has happened to this. So all I need to do, and this is easier than plugging it all back into the rate equation, which you could do, is just find out what's happened to this. So I want to do 8.25 times 10 to the minus 11 divided by 2.75. And what is that going to give me? Multiplied by 3 times from there to there. And therefore, what could have caused that? Well, it wasn't the propanone. It's definitely not the bromine because it's 0 order. It's not the propanone because it stayed the same. So this must have tripled as well. So you're going to do 2.5 times 10 to the minus 2. You're also going to multiply that by 3, and you're going to get 7 1.50 times 10 to the minus 2. Now that's going to get you another mark. And then we're going to look down here at experiment 3, and we're going to say, well, what has happened to the rate? Well, let's check it out, check it out, check it out now. So what have they done with all of these? What has happened? We're at 8.25 times 10 to the minus 11. It doesn't matter what's happened to the bromine, so we can forget about the bromine. If you want, you could put a fat line through the bromine and say, right, I'm not interested, because that is zero order. It has no effect on the rate. So we just want to look like, okay, what has happened here to the propanone? Well, it was 1.5 times 10 to the minus 2. So let's see what's happened to the propanone. Well, we're going to divide 3 point. Oh no, we're going to divide. It's gone down, hasn't it? Look, it's to the minus 3. So the propanone has got less. So it's gone from 1.5 times 10 to the minus 2. Now I want to divide that by 3.75 times 10 to the minus 3. What a bummer. Let's do that. 1.50 times 10 to the minus 2 divided by 3.75 times 10 to the minus 3. And that tells me it's got 4 times less. So that is 4 times less. So that means that compared to the initial rate of 2.75 times 10 to the minus 11, my first effect is that this has been divided by 4. So the initial rate will have also gone down by 4. So let's put it in as 2.75 times 10 to the minus 11, and let's divide it by 4. And that tells me that it should be 6.875 times 10 to the minus 12. So if this also here goes down by 4, divided by 4, and that's because that's first order. So if that's divided by 4, then this has to be divided by 4. Then it would go to 6.875 times 10 to the minus 12. Now, that's not my final answer. If I put that, I'm not going to get the mark. Why is that? Because I haven't looked at what's happened to this. What's happened to this? Just to confuse things even more, they've increased this. How much have they increased it by? Well, this is to the minus 1 and that's to the minus 2. So I need to divide that by that to find out how much they've increased it. I believe they've increased it by 4. So we're just going to be going back, but let me just double bubble check that. So 1 times 10 to the minus 1 divided by 2.50 times 10 to the minus 2 equals 4. What a bummer. They divided by 4 and times by 4. So we're actually going to have the same rate. So what they've done with this one, from here to here, they have times by 4. So I know I divided by 4, but I need to go ahead and times that by 4. And guess what? Divide by 4 times by 4, it's going to take us back to 2.75 times 10 to the minus 11. And there we go. That is going to be our last mark of that. Now, that was a bit of a brutal opening to this test paper, but that's a 5 marker. Let's move on and do the rest of this question. Okay, so we have the last couple of bits of this question. 1.3, figure 1 shows an incomplete mechanism for this reaction. We have propanone, we have a hydroxide ion, we have step 1. Okay. Then we have step 2. You can see bromine, a pair of electrons going from that double bond to the bromine, and that is step 2. Complete the mechanism in figure 1 by adding 4 curly arrows and any relevant lone pairs of electrons. That's 4 marks. Let's go. Pause the video, scribble it down on paper, then unpause and see if you got it right. Okay, so I'm going to go through what we got to do here. Let me pick another color. Let's go pink because we love it. Oh, maybe not. All right, let's forget about that. Right, let's go. So what we want to do is, first of all, look at step 1. Now, how do you work out what's gone on? Check this out. Focus on that. What is the difference between that part initially and after, before and after? That's what you want to do. So hopefully you've spotted something has gone on here. Between the COO has gone to CO, and that has gone minus. So what's actually happened here is a pair of electrons have gone here from the double bond to there, and that is going to make that have a lone pair and be negative. Lovely. Something else has happened. This hydroxide ion has bonded to the hydrogen. Now, what group is hydrogen in? Well, it's technically got 1 electron. It's got 1 electron in the 1s orbital. It can't already have a full 1s orbital here and then accept another electron from the hydroxide ion, or the pair of electrons from that. That would then make it have a 1s2 and a 2s2. It can't have that. It can only have 2 electrons in the outer shell in the old GCSE ring system. So hydrogen is essentially a group 1 element. It can only have 1 bond, 1 covalent bond, which means this needs to split. And what's going to happen there? Well, this, we can look again. What's the difference? Look there, look here, a double bond has formed. And so that has happened because the hydrogen has donated its pair of electrons there, like that. That's the worst curly arrow in the history of mankind, but from there to there, and that's what's given us that double bond. So what we've got going on is 2 curly arrows, and really that should be a lone pair there, because that gained a little lone pair, that oxygen, and gave it a negative charge. Now let's go down here and see what's the difference over here. Again, we want to focus on what the difference is. Check it out now. Check it out now, right? So the double bond has reformed. So we just got to reverse that process. We want to show that lone pair, and we want to show that lone pair is reform. Oh my gosh, I can't draw a circle. We want to show that reforming, right? So that is going to reform that double bond. Now, this here has gone single again, and it's gone single from double. So what we need to do is, well, we don't need to show that because that has been shown. But bromine's in group 7, a bit like hydrogen in group 1, it can only have 1 covalent bond at any one time. Therefore, as a covalent bond is forming here, this bad boy must break. So that's what we want to show there. And there's one more lone pair to draw on, and I guess you can guess where it is. The bromine is negative, but it has a lone pair. And there we go. We've got 1, 2, 3, 4 curly arrows, and they told us to do 4 curly arrows in any relevant lone pairs of electrons. We've got 1, 2, 3 lone pairs. So that is going to get you 4 marks, which is quite nice. Use evidence from the rate equation to explain why step 1 is the rate determining step. So why is this the rate determining step and not step 2? If you remember our rate equation, I'm going to type it out for you. Remember our rate equation, as you can see here, bromine does not appear in the rate equation. So that immediately puts us off that. The slow rate determining step will feature all the reactants in the rate equation. Well, it features propanone and hydroxide ions. So for life, let's write that again. Okay, so both reactants in step 1 appear in the rate equation in the correct amounts as shown by the rate equation. Oh my gosh, that was just disgusting. Oh, doing these videos is so long because my fat fingers are so bad at typing. But there we go. That's the end of that question, folks.
You're still here? It's over.